Okay, in this video I will say a little bit about symmetric and skew-symmetric matrices. And this is about square matrices. So a square matrix M, let's say an n by n matrix. Well, we don't need to use n to define it. A square matrix M is symmetric if its transpose is equal to itself. That's the first definition, symmetric matrix. And a square matrix, say N, is called skew-symmetric. Skew-symmetric is sometimes called anti-symmetric. Skew-symmetric if its transpose is minus itself. It's the additive inverse of itself. So let's look at some examples. So if you have this matrix A, which is 0 to 4 to 1, 3, 4, 3, like pi, okay, this is in fact a symmetric matrix. Because when you transpose, you're switching the rows and columns. You're making a new matrix whose ith row becomes the ith column, and the ith column becomes the ith row. And you can actually see that when you take the transpose of A, you get A. Now notice that when you're writing down the matrix and you want to make it symmetric, once you write down the 1, 2 entry, right, then the 2, 1 entry has to be equal to it. However, you do have freedom when you're writing down a symmetric matrix of what the diagonal entries are. I mean, the diagonal entries can be anything. And it's just that once you declare that, you know, the entries here are going to be 2, 4, and 3, you're declaring that these entries have to be 2, 4, and 3. They have to correspond to the entries here to make the matrix symmetric. Okay, let's do an example of a matrix that's skew-symmetric. So let's say I have this matrix A, which is 0, 2, 4. Well, when I make the transpose, see A transpose is going to be like 0, 2, 4 here. So if I want the transpose to be negative A, I'm going to have to make this a negative 2. And I'm going to have to make this a negative 4. Right? Because I want A to be negative this, and then there's going to be a negative here and a negative here. Oops. Now, if you think about that, can I have a skew-symmetric matrix where this diagonal entry is like 3? Well, if you think about it, the answer is no, because when you do the transpose, that 3 is going to be a 3 here in the transpose, but then A transpose has to be negative A. Remember, when you're taking negative A, you're multiplying every single entry by negative 1. And so, you know, if you have A is, if this entry is 3 and then A transpose is 3 here, there's no way A transpose can be negative A, right? And so for a skew-symmetric matrix, all the entries on the diagonal actually have to be 0. Okay, now I have some choice for the other entry. So let's say I make this a negative 1. Well, what does the entry here have to be? It has to be 1, because when you write down the transpose, so you're going to have negative 2 here and negative 4 here, this negative 1 here, when you transpose, it's going to go down here, and then A transpose has to be negative A, and so that forces this entry here to be 1. Okay, okay, so now we just successfully wrote down an example of a skew-symmetric matrix. So A is skew-symmetric. Because A transpose, which is this, is equal to negative A. That's what skew-symmetric means. Right. And in terms of the entries, if you call your matrix A, let's call the entries Aij, then A is symmetric if Aij is just Aji for all I and j, and it's skew-symmetric if Aij is negative Aji for all I and j, and Aii is 0 for all I. Okay, that's one way to phrase symmetric and skew-symmetric. Now it turns out that every matrix, now of course not every matrix has to be either symmetric or skew-symmetric, right? I mean, in general, if you have a random matrix, its transpose will not be the original matrix, and it won't be -1 times the original matrix either. However, every square matrix, so the theorem is, every square matrix A can be written in a unique way, uniquely, as the sum of a symmetric matrix and a skew-symmetric matrix. And this is sometimes useful to know. It sometimes reduces certain proofs to the case of a symmetric matrix. If you can somehow show that somehow the skew-symmetric part, so to speak, is not relevant. Okay, let's prove this. So first of all, let's show existence. Okay, so we want to express A as m plus n, where m is symmetric and n is skew-symmetric. So we can actually say what the matrix is. We define m to be 1/2 of A plus A transpose, and n to be 1/2 of A minus A transpose. Now I claim that m is symmetric. M is symmetric because, well, what happens if you take the transpose of this matrix? You just get 1/2, and then you take A plus A transpose. When you transpose this, so first of all, the 1/2 is not relevant. You can pull it out, right? If you take half of a matrix and then transpose it, that's the same as transposing it and taking half of it, because you're just multiplying each entry by 1/2. Now, when you have 1/2 of A plus A transpose, we can use the properties of transpose, right? We're using the property that if you have A plus B transpose, it's A transpose plus B transpose. In particular, this is going to give you A transpose plus A transpose, right? That's what this fact gives you when you apply it to B equals A transpose. And what happens when you take A transpose and transpose it? Well, if you transpose a matrix and then transpose that, you just get back the original matrix. So you're going to get A. And what is this matrix? 1/2 of A transpose plus A is M. So therefore, we show that M transpose is in fact equal to M. So M is symmetric. Okay. And let's check similarly that N is skew-symmetric. Well, N transpose is 1/2 A. I mean, the proof is, you can probably see what's going on, right? There's a minus sign here. So when you transpose this is going to be 1/2 A transpose minus A transpose transpose. This is 1/2 of A transpose minus A, which is exactly equal to negative n. So that shows that n is skew-symmetric. And we can see that A is in fact equal to m plus n because m is 1/2 A plus A transpose, n is 1/2 A minus A transpose. This is equal to 1/2 A plus 1/2 A transpose plus 1/2 A minus 1/2 A transpose. The 1/2 A transpose is canceled. You get 1/2 A plus 1/2 A is A. Therefore, we've written A as a sum of a symmetric matrix and a skew-symmetric matrix, and that proves the existence part of the proof. Okay, now we need to show, so we now know that whenever you have a matrix, a square matrix, it can be written as the sum of a symmetric matrix and a skew-symmetric matrix. That's what we've shown. However, how do we know that there isn't some other way to do it, right? We know that we can take the symmetric one to be half of A plus A transpose, and the skew-symmetric matrix to be 1/2 of A minus A transpose, but how do you know that there isn't some other combination of symmetric and skew-symmetric matrix that will somehow combine to make A? So this leads us to the uniqueness part. So suppose that A is equal to, do I want to use M and N again? I could, but let's say that A is equal to M1 plus N1, where M1 is symmetric and N1 is skew-symmetric. Okay. We want to show that M1, so we suppose that we have a decomposition of A as a sum of a symmetric and a skew-symmetric matrix. To show uniqueness, we need to prove, so we want to show that M1 has to be 1/2 of A plus A transpose, and N1 has to be equal to 1/2 of A minus A transpose. And if we show that, then we show that there's only one way to decompose A into a sum of a symmetric and skew-symmetric matrix. Well, this is a problem involving transposes. So, I mean, if A is M1 plus N1, well, what happens when you transpose? You get M1 transpose plus N1 transpose. Now, M1 is symmetric, and so how do we write this? M1 is symmetric and N1 is skew-symmetric. So, therefore, this is equal to M1 minus N1. Right? So now we have these two equations. We have A is M plus N, and we have A transpose is, or M1 minus, sorry, I have the ones. M1 plus N1. A transpose is M1 minus N1, and now you see what we can do. We can add them, and the M1s are going to cancel, and so you get A plus A transpose is equal to 2M1. I mean, this is like solving a system of equations, right? And so therefore M1 has to be, you can divide both sides by 2, 1/2 of A plus A transpose. So actually, that's the only symmetric matrix that can work. And so now we have M1, and so therefore N1 is, well, we know that that's A minus M1, and that's A minus 1/2 A plus A transpose, which is precisely going to be 1/2 A minus A transpose. And so therefore, there's only one way to split up A into a sum of a symmetric and skew-symmetric matrix. So proving uniqueness. Okay, and that's the proof. So let's just do a quick example. So let's say that A is this matrix 1, 2, 3, 4. Well, this is certainly neither symmetric nor skew-symmetric, right? If you just take the transpose, the 2 and the 3 get mixed up, they get switched, and okay, A transpose is not A. A transpose isn't negative A either. So what is A transpose? A transpose is going to be this. No, that's A. I'm writing down A. Okay, nope. This is A transpose. There we go. And so A plus A transpose is going to be 2, 5, 5, 8, right? And so M is going to be 1/2 of that. That's going to be 1, 5/2, 5/2, 4. And this is in fact symmetric. And now to figure out what n is, we just do a minus m, right? N is equal to a minus m, and that's going to be 1, 2, 3, 4, minus 1, 5/2, 5/2, 4. And this is going to be 0, negative 1/2, 1/2, 0. So we have A, which is 1, 2, 3, 4, equals, the unique decomposition is into a sum of symmetric and skew-symmetric matrices is 1, 5/2, 5/2, 4, plus 0, negative 1/2, 1/2, 0. Yeah, it all checks out. That's A, that's M, and that's N. Easy. Okay, I hope you found this video helpful for understanding symmetric and skew-symmetric matrices. Thanks for watching.